Hey everyone, welcome back. Today we'll solve one of the classic computer science problems, House Robber, Leetcode 198. This problem is part of Blind 75, a curated list of essential coding interview questions. You can find the full list linked in the description below. Be sure to check it out. Now to the problem. In this problem, we are working as a professional robber planning to rob houses along a street. Each house has a certain amount of money stashed. The only constraint stopping you from robbing each of them is that adjacent houses have the security systems connected, and it will automatically contact the police if two adjacent houses were broken into on the same night. So our task is, given an integer array nums representing the amount of money of each house, return the maximum amount of money we can rob tonight without alerting the police. Then in example 1, in the given nums array, once we rob the house with money 1, we cannot rob the house with money 2, but we can rob the money from house with money 3 and 1. And if we rob the house with money 3, the total number of money we will rob will be 4, and that is the maximum money we can rob. So total robbed money in this case will be 4. Similarly, in example 2, for the given houses with different amounts of money, the maximum amount of money we can rob is 12, which we can get, for example, by robbing the houses 1, 3 and 5. Now in terms of solution, one of the naive approach can be that we compute the largest possible amount of money we can rob by explicitly examining all potential combination of houses. So the idea is simple. For every house, we have two possible choices. Either we rob the house or we skip it. And if we rob the house, we can add the amount of money from that house to the total and skip the adjacent house. But if we don't rob the house, we do the same thing from the next house and take the maximum amount of money between the two choices and continue the examination recursively for the rest of the houses. For example, here for house 0, we have the amount of money as 2. So either we can rob it or skip it. Now if we rob it, we cannot rob house number 1. Instead, we can now rob house number 2. Now, again at house number 2, we have two choices. Either to rob it or skip it. And if we rob it, we cannot rob house number 3, but we can rob house number 4. And again for house number 4, we have two possible choices, whether to rob it or skip it. And if we rob house number 4, there are no more houses left, so we have hit the base case. Hence, the total amount of money we can rob at this point will be 1. Similarly, if we skip this house 4, the total amount of money we can rob will be 0 because there are no more houses remaining to rob from. And we have to return the maximum amount of money we have robbed so far. That is maximum of 1 or 0, which will be 1. And now the total amount of money we can rob starting from house number 2 will be 10. But if we skip house number 2, then we will rob house number 3. And again we will have two possible choices, either to rob it or skip it. Now if we rob house number 3, we cannot rob house number 4. And again we hit the base case as there are no more houses remaining to rob from. So the maximum amount of money we can rob at this point will be 3. And if we skip house number 3, we will again rob from house number 4, where again we can rob it or skip it. And this we are seeing as a repetitive problem because we have already calculated the value for robbing from house number 4 as 1, which we will return here. And here we are unnecessarily recalculating it instead of reusing it. But let's continue. And again the maximum loot starting from house number 3 will be 3, and the maximum rob we can return to house number 0 will be 10. So the loot we can collect starting from house number 0 will be 10 plus 2 equal to 12. But we have another part to consider where we will skip house number 0 and try starting robbing from house number 1 instead. And again we will have two possible choices, either to rob it or skip it. Now if we rob it, we cannot rob house number 2, but we can rob house number 3 instead. And again we can rob it or skip it. Now if we choose to rob it, we encounter a repetitive problem because we have already solved it here, which resulted in loot of 3. So we will return 3 from here. And if we skip it, we will try to rob house number 4. which again is a repeating problem for which the loot amount is 1 and hence the maximum loot we can rob starting from house number 3 will be 3 and the total robbed amount if we loot house number 1 will be 10. Similarly, if we skip robbing the house number 1, we will rob the house number 2, which again is a repeating problem with loot amount equal to 10. So the maximum value we can loot starting from house number 1 will be 10. And finally, the maximum loot amount starting from house number 0 will be maximum of 12 and 10, which will be 12 in this case. And mathematically speaking, if rob I represents the amount of money robbed starting at house I, then it is calculated as the maximum of two choices, where first we rob the current house, which includes the money amount, nums I, and the result of skipping the next house, that is rob of I plus 2, or we can skip the current house and start robbing from the next one, which is rob of I plus 1. And this is how we were breaking down the problem into smaller ones during our recursion flow. Now the time complexity of this approach is O of 2 to the power of n, where n is the number of houses, because for each house we create two recursive calls, whether to rob it or skip it, leading to exponential growth in the recursion tree. And the space complexity will be O of n, mainly coming from the depth of the recursion, which is equal to n, since each recursive call processes one house at a time. And as we observed during the dry run of the naive approach, there were many repeating subproblems. For example, we were calculating the loot amount for houses 4, 3 and 2 multiple times. So to optimize this, we can use memoization or caching. We can create a cache to store the results for each house. And now whenever we process the ith house, we first check if its result already exists in the cache or memo table. If yes, then we return the result directly. Otherwise, we compute it and store it in the cache to reuse it later. And now the time complexity reduces to O of n because each house index is computed only once and stored in the cache, and the space complexity stays O of n due to the recursion stack and the cache to store up to n results. For the code implementation of the recursive and top-down dynamic programming approach, please refer to the link provided in the description below. Now let's solve this problem using bottom-up dynamic programming approach. This approach eliminates recursion by iteratively solving the problem from the smallest subproblems to the larger ones. In the bottom-up dynamic programming approach, we use tabulation by creating a DP array to store the intermediate results. In this array, DPI represents the maximum amount of money that can be robbed up to the ith house, that is from house 0 to house number I. Now, first let's look at the base cases. At I equal to 0, we consider the loot from house 0. For the 0th house, what is the maximum amount of money we can rob? The answer is 2, as it is the only option. So DP of 0 will be 2. Next, let's look at I equal to 1. And now we have two houses to rob from. Either we can rob house 0 and skip house 1, or we can rob house 1 and skip house 0. Since we cannot rob from adjacent houses, but we want to rob the maximum amount. So DP of 1 will be maximum of 2 and 7, which is equal to 7. So we will rob from house 1 and skip house 0 and move the iterator I forward to 2. And from here on, the interesting cases arise where we consider robbing from 3 or more houses. So here we will have two choices. Either we can rob this house, which will give us the amount 9, but now we cannot rob from house number 1. Instead, we can take the maximum loot we have collected so far from the non-adjacent houses 2 steps behind, which is DP of 0, resulting in total of 11. Or we can skip this house and take the maximum loot up to the adjacent house 1 step behind, which is DP of 1 equal to 7. And between 11 and 7, we choose the maximum again, which results in DP of 2 equal to 11. And again we move the I pointer forward. Now I is equal to 3. And again we have two choices. Either to rob the current house, which gives us a loot value equal to 3, plus collect the maximum loot from the non-adjacent houses, which is DP of 1 equal to 7. Or we can skip the current house and collect the maximum loot up to the previous house, which is DP of 2 equal to 11. And again, we try to maximize the loot, which will give us DP of 3 equal to 11. and again we move the I pointer forward. Now I is equal to 4, and again we will have two choices, either to rob the current house, which gives us the loot value equal to 1, plus collect the loot from the non-adjacent houses, which is dp of 2 equal to 11, or skip the current house and take the loot up to the previous house, which is dp of 3 equal to 11, and again maximizing the loot value for dp of 4 gives us 12, which corresponds to the maximum loot from all the houses. Hence, we will return 12 as our answer. And the dp recurrence relation to calculate dp of I can be written as maximum of robbing the current house and collecting the loot of nums I plus maximum loot from non-adjacent houses, which is dp of I minus 2, or skip the current house and take the maximum loot from the previous house, which is dp of I minus 1. Now the time complexity of this approach is O of n, as filling in the dp array requires iterating through all the n houses, and the space complexity will be O of n as well to store intermediate results in the dp array. But do we really need to use O(n) space for this problem? If we look closely at the recurrence relation, each result dp of I depends only on the previous two values, which are dp of I minus 1 and dp of I minus 2. So instead of maintaining a full dp array, we can optimize space by using two variables, previous one to represent dp of I minus 1 and previous two to represent dp of I minus 2. This approach is similar to other problems we have seen in the past, like generating the nth Fibonacci number. And as we iterate through the houses, these two variables are dynamically updated to compute the result. And by eliminating the need for the full dp array, the space complexity reduces from O of n to O of 1, while the time complexity remains O of n. Here is a quick code walkthrough of the algorithm we just talked about, with Java code on left and Python on right. First, let's get total number of houses. Let it be n. Now let's handle the case when there is only one house. In that case, we can rob it and directly return its value as the maximum loot. Now let's initialize the base variables, which are previous to denoting dp of I minus 2 initially equal to dp of 0, representing the maximum loot for up to house 0, which is equal to num 0, and previous one, which is equivalent to dp of I minus 1, initially equal to dp of 1, representing the maximum loot for up to house 1, which is equal to maximum of num 0 and nums 1. And now that we are done with the base cases, we can iterate through the houses starting from index 2 and calculate the loot value for the current house, which is maximum of two choices, where we rob the current house and take its value nums I and add the loot from non-adjacent houses, which is previous to, or we skip the current house. In that case, we take the maximum loot obtained up to the previous house, which is previous one, and take the maximum of these two loots. And once we are done, we update previous two and previous one to previous one and current respectively, and continue with the iteration until we are done with all the houses. And after the loop finishes, previous one will hold the maximum amount of money that can be robbed from all the houses, which we will return as our answer. So that's all for this video. I hope this video was useful to you. If it was, please give it a thumbs up and share it with others who might benefit from it. If you haven't subscribed the channel yet, make sure to hit the subscribe button and turn on the notification bell so that you never miss an update. Your support helps me create more content like this. If you have any questions or suggestions, feel free to leave them in the comments below. Thanks for watching and see you in the next one.